Okay, I'm going to talk you through how to do Verilog for finite state machines without giving you exactly everything that you need. Let's say I have three states, A, B, and C. And from A, if I get a 1, I go to B with a 0 output. If I get a 0, I go to C with a 1 output. From B, if I get a 1, I go to A with a 0 output. If I get a 0, I go to C with a 1 output. And from C, if I get a 1, I go to A with a 0 output. And if I get a 0, I go to B with a 1 output. So A, B, C, next state, W equals 0, W equals 1. For A, W equals 0, I go to C. W equals 1, I go to B. B, W equals 1, I go to A. W equals 1, I go to A. W equals 0, I go to C. For C, W equals 1, I go to A. And W equals 1, I go to A. And W equals 0, I go to B. And for B, W equals 0, I go to C. Is that right? And then for my output, from A, if W equals 0, my output is 1. If W equals 1, my output is 0. B, 0, it's 1. 1 is 0. And C, 0, it's 1. And W, it's 0. Okay, I shouldn't do that. Let me make that 0 and 1. Alright, so then how am I going to set this up to code this? Well, first of all, I need to make sure that I assign all my states. So I would have A equals 0, 0, B equals 0, 1, C equal 1, 0. I do need to make sure that I take care of my don't care state, and you'll see how to do that when we get to the code. So this is not exactly the program that you're going to be doing, but it is similar. Okay, so the idea is that you will have an input, that's your clock. You will not have an input L. I'll have an input W. We're not going to have an input S. We'll have an output reg Z, and we'll have an output reg that will be our present state. I'll just leave it to no, I'm not going to do that. I'll have it go 1, 0. I like that better. Then I'm also going to have my next state is going to be a reg, and I'll have that be 0, 1. And then I will have some parameters, or 1, 0. 1, 0. And the reason for that is I had 3 states, and so I will need at least 2 bits to represent those. I will represent these as parameters, A, B, and C, just because it'll make it easier for me to think of them in terms of A, B, and C rather than their binary equivalents, although sometimes that's just as easy. Okay, so now I'm going to have an always block, and in this always block I'm going to say what my next state is. I prefer to do it like this. There, I like that. Okay, so now, always at Z in my present state. So anytime I change my input or my present state, I'm going to do this always block. But I don't go to my next state until my next always block. And you'll see what I mean by that in a minute. You're going to have two always blocks. And so you're always figuring out what your next state is going to be, but you don't actually assign that until later. And I actually want to have two let's see, yeah, I'm gonna have another thing here. I'm gonna have reg next Z, because I'm going to want Z to be the light that's lit up, and I don't want that to change until I get to the next clock cycle. Because the example that I had here was a Moore machine, and you're doing Mealy. So, all right. So now, we can have our case based on either what our input is or what state we're in, because everything depends on both of those. So we'll do it by the present state. So if we are in state A, if our input is 0, so let's take a look at our diagram. If we're in state A and our input is 0, then our next state is C. Also, we have two things here. Also, our next Z is 1. So that's if W equals 0. Else, Let's see, what do I have? Oh, capital C. Okay. Else, so now if I'm in state A, if that means my input was 1, then my next state is B and my output is 0. And that's the end of case A. So what I did for case A is I had begin, and if W equals 0, then I said what my next state was and what my next Z was going to be. And then if W was equal to 1, then again I did the next state, and so forth. And that's the end of case A. And then I would do the same for case B. So and for B, if W equals 0, my next state is C and my output is 1. Else, next state is A, output is 0. Okay, I'm not going to go through all of those, but you would do that. And then the other thing you need to make sure, since we only had 3 states for your case statement, you need to make sure you have a default. So in addition to the states, that A, B, and C, you need to have a default because you have some don't cares in there. So doesn't matter what you do. You can make them don't cares if you want. It doesn't really matter. Okay, but then here's the next part that you have to do. So you're going to end that case and you're going to end that always block. But you're going to have another always block. And your other always block is going to be based on the clock. And so you're going to have always at positive edge clock. And what this one's going to do is it's going to actually advance your machine. So in the other part you were just defining what the next state and what the output were going to be. Here you actually make it change. So here you will have your always block always at the positive edge of the clock. You're going to make your present state equal to your next state, and you're going to make Z equal to your next Z. And then end. And then it's going to be your Z that you put in your constraints. So in your constraints, you need to have your output. Your Z is going to be attached to a light. You're going to need to have your W is going to be a switch. You're also going to need to set up your clock. And your clock, you get that, you can just look at it right here. You also had it in your, it says, you have the information about the clock also right here. There we go. To use a button as a clock signal right there. Alright, I hope that's helpful.